All right, to start off, suppose we have a function y equals f of x, and we have some subinterval I on the domain of f of x. Later on, we say that f is increasing on the subinterval I if f of x sub 1 is less than f of x sub 2 for all x sub 1 less than x sub 2 on the subinterval I. Okay. So what is this saying? Well, the best way to understand what this is saying is to draw a graph. Okay. All right, so suppose that I graph a function and it looks like this. And I choose two unique points on the graph. This point is x sub 1, y1. And this point up here is going to be x sub 2, y sub 2. If I project this point down to the x-axis, I hit the tick mark x sub 1. If I project this point down vertically to the x-axis, I strike the tick mark x sub 2. If I project this tick mark horizontally back to the y-axis, I strike f of x sub 1. If I project this horizontally back to the y-axis, I strike f of x sub 2. We understand this graph so far. Right. All right, so ladies and gentlemen, we say that this function is increasing on some interval I that contains x sub 1 and x sub 2. This is some subinterval of the domain of the entire function here. Okay. And on this subinterval, we say the function is increasing if it is true that f of x sub 1 is less than f of x sub 2, and that's clearly the case. This is less than this whenever x sub 1 is less than x sub 2. And clearly x sub 1 is less than x sub 2 on the x-axis. We say the function is increasing. Now, another way to think about why the function is increasing on this interval here is if we progress from left to right in the xy plane, we're on this graph here, but we're rising. You agree? We're rising up higher on the graph. That's to say the function is increasing. As we move from left to right, if the points on the graph are moving upwards, rising, the function is increasing. Another way to think about why this is increasing is if I was to choose any point in the subinterval I on the graph and then draw a line that is tangent to the graph at that point. What does it mean for a line to be tangent to a graph at a single point? Well, that means this tangent line, this line only touches the graph precisely at that one point. And this is called a point of tangency. So for any point we choose in the subinterval I on the graph, we can see that a tangent line to the graph at that point is a rising line. And rising lines always have positive slopes. And for that reason, that's another reason why we would say this function is increasing on the subinterval I here. Okay. So this is what it means for a function to be increasing here. Any questions about that? All right. In a similar fashion, we say that f is decreasing on our subinterval I if f of x sub 1 is greater than f of x sub 2 for all x1 and x2 on the subinterval I. And again, graphically, we will be able to appreciate this, what it's saying. So I'm going to graph this and breathe life into this this definition here. All right, suppose I have the graph of a function and it looks like this. And I choose two different points on my graph. I'll call this point x1, y1, and designate this as x2, y2. Projecting this point vertically down or perpendicularly down to the x-axis, I strike the tick mark x1. Projecting this up perpendicular to the x-axis, I strike the tick mark x2. Projecting this point horizontally back to the y-axis, I strike the value of f of x sub 1. Projecting this point back to the y-axis, I strike the value f of x sub 2. And if I enclose these two numbers, x1 and x2, in some sort of a subinterval, I, that is a smaller subset of the entire domain of this function, we can see that this function is decreasing on the subinterval I. Why? Because it's pretty obvious that f of x sub 1 is greater than f of x sub 2 on the y-axis. Do you agree this number is greater than this number on the y-axis? F of x sub 1 is greater than f of x sub 2. And it's also true that x sub 1 is less than x sub 2 on the x-axis. We say that the function therefore is decreasing on the subinterval I here. Another way to think of why it's decreasing is think about this as we progress strictly from left to right in the plane. If we're on this graph, in this subinterval, we are falling down on the graph. We're falling, not rising on the graph. That's another reason why to think that this function is decreasing on the subinterval. Another way to think about why it's decreasing is for any point I choose on the graph in the subinterval I, if I draw a tangent line to my graph at that point of tangency, you can see that this is a falling line, and falling lines have negative slopes. And for that reason, we say that this function's graph is decreasing on the subinterval here. Okay, any questions about that? We say that f is constant on our subinterval I if f of x sub 1 is equal to f of x sub 2 for all x1 and x2 on our subinterval. Okay. By the way, for decreasing up here, not only did x1 and x2 have to be on a subinterval, but x sub 1 had to be less than x sub 2 in this situation here for the decreasing case here. Okay. All right, constant function. Let's try to illustrate what it looks like for a function to be constant on an interval. I got x1 and I have x2 on some subinterval here, I. And okay, some subinterval I. And suppose that my graph of my function looks like this. Okay. All right, we can see that for all x1, x2 in the subinterval I, that it is obviously true that f of x sub 1 is equal to f of x sub 2. And that's why we say this function is constant on the subinterval here, I, that contains x1 and x2. In other words, wherever your graph of your function goes horizontal, that's where it remains constant on that interval. Okay, so this is the constant nature of this graph here on the subinterval. Any questions about that? What it means to be constant? Well, we looked at what it means for a function to be increasing or decreasing or constant on an interval. All right. All right, let's look at a particular example here. All right, suppose that I have the graph of a function that looks like this. All right, and so, ladies and gentlemen, I have a graph of a function, and I am interested in indicating what intervals this function is increasing. So on what interval is this function increasing? Well, from left to right as we move in the plane, on what part of the graph are we rising from left to right? Well, it would just be this portion of the graph here. We're rising up higher on the graph. So we would say that our function is increasing on the interval. This goes forever that way, from negative infinity up to positive 2. So the function is increasing on the interval from negative infinity up to 2. That's the interval in which the function is increasing.
When we're writing this, are we gonna need to use like the brackets, or is it always gonna be like the parentheses?
Parentheses, these are always going to be open intervals, okay? All right, now f of x is going to be constant on what interval? On what interval is this function constant? Well, where does the graph go horizontal? Where on this graph do the y coordinates remain the same as we progress from left to right on the graph? That would be right here. We have a horizontal portion of graph. So it looks like on the interval from 2 to 7, our function is constant. Finally, on what interval is our function decreasing? Well, as we progress from left to right on the graph, where do we fall on the graph? We fall on the graph right here in this interval, falling down. So it looks like from 7 to positive infinity, the function is decreasing. Does that make sense, sir? You can think of it this way also. On this interval, for all real numbers less than 2, no matter where you put a point on this graph, a tangent line that touches a graph at that point will always be a rising line. And because of that, their slopes are always, the slopes of these rising lines are always positive. That indicates the function is always increasing on this interval. As soon as we choose points on the interval from 2 to 7, then our tangent line becomes horizontal. And the slope of horizontal line is 0, meaning there's 0 change in y with respect to x, meaning the function is constant on this interval. If we choose any point on the interval for any real numbers greater than 7, our tangent line that strikes the graph is a falling line, and falling lines always have negative slopes to them. Okay, and that's why our function is decreasing on this interval here, 7 to infinity. Any questions about that there? All right, so it's pretty easy to determine on what intervals a function is increasing versus decreasing. Again, always go from left to right and move from left to right on the graph. Where you rise on the graph, you're increasing. Where you're staying constant on the graph or horizontal, you're constant. Where you are falling on the graph, the function's decreasing. Okay. All right, the next thing that we're going to look at is what is called relative, or sometimes some textbooks refer to it as local extrema of a graph. All right. Suppose I graph a function and it looks like this. Okay. I'm going to call this point here a f of a. I project this horizontally back to the y-axis. I strike f of a. This is a on the x-axis. All right. We say f of a is a relative or local. Some books call them relative, some call them local. Maximum of f of x. Suppose I enclose this value a in some sort of small interval. I'll call it interval I sub 1, which is a little subinterval of the domain. It's a subset of the domain of this entire function. It's just some small little interval that contains this value x equals a. So we say that f of a is a relative or local maximum of f of x if there exists an open interval. Open interval means you got parentheses on the left and the right. That's an open interval, no brackets. On an open interval containing a, containing x equals a, such that f of a is greater than or equal to f of x for all x not equal to a in the subinterval I sub 1. Okay. So what's it saying? Well, it's saying this: if I choose some other value in this subinterval other than a, like if I choose x sub 1 here, x sub 1, and if I project x sub 1 up till I hit the graph, and I'll hit the graph like right here, then I'll project it horizontally back to the y-axis, and I strike f of x sub 1 here. Do you agree, ladies and gentlemen, that f of a is greater than f of x sub 1? F of a is greater than f of x sub 1. That's true, isn't it? Suppose I go a little bit to the right of a and choose some value x sub 2 in the subinterval I sub 1. Project it up and hit the graph, maybe right here. Project it back to the y-axis. I get suppose f of x sub 2 is equal to f of x sub 1. Just so happens this is the way it works out. You can see that f of a is still greater than f of x sub 2. That's why we classify the point f of a as being a local or relative maximum. Think of it this way: this point f of a is the highest point on the graph in this little local neighborhood or local vicinity here, or little local interval. All right, because if you go a little bit to the left of this point f of a, you fall down on the graph. You're a little lower than this point. You go a little bit to the right of this point on the graph, you fall down to a point that's a little lower than this graph. That's why we classify this point as being a relative or local maximum for f of x. Does that make sense? And in a similar fashion, suppose I choose this point down here and its ordered pair address is b f of b. All right, and suppose I enclose b within some sort of small subinterval called I sub 2. So we say f of b is a relative or local minimum. Relative or local minimum of f of x if there exists an open interval containing x equals b such that f of b is less than or equal to f of x for all x not equal to b on the subinterval I sub 2. That's what it means to say that we have a relative or local minimum at some value x equals b. That's to say that if I choose some value in the subinterval I sub 2, that is a little bit to the left of x equals b, like maybe x sub 1, project it down, I hit a point on the graph, and then project this back to the y-axis, this will be f of x sub 1. F sub b projected back to the y-axis is going to be down here. You can see that f of b is less than f of x sub 1. Or if I choose some point in the subinterval over here called x sub 2, hit the graph right here, project it back to the y-axis at f of, and I got f of x sub 2, you can see that again, f of b is less than f of x sub 2. So in other words, you could think of it this way. If you move a little bit to the left on the graph from this point b, f of b, you are a little higher on the graph than this point down here. Likewise, if you move a little bit to the right, you're a little bit higher on the graph than you are here. That's why we classify this as being a local or relative minimum of f of x. And it occurs at x equals b, and it is f of b. Okay. So I've defined for you what a relative or local maximum is and a relative or local minimum of f of x. Okay. Together, these are called relative or local extrema. So a relative minimum or relative maximum belong to a class of points on a functions graph called relative extrema. Okay. All right. Now, when you get into calculus 1, you're going to learn about the derivative in calculus and how to differentiate a function and how that can be used to identify the location of relative extreme on a graph very easily. You do that in your first semester of calculus. Okay. All right. Suppose I have the graph of a function. It looks like this. Okay. Suppose I have a graph of a function that looks like this. All right. Actually, I'm going to extend this graph down here a little bit. Down here too. Yeah. All right. We say at this point here, f of a, we say that f of a is an absolute maximum of f of x. Since f of a is greater than or equal to f of x for all x on the domain of function f of x. Okay. An absolute maximum is the absolute highest point on the graph. That's the highest point on this graph right there. There is no point higher on this graph than this point. That's called an absolute maximum. This point is also a relative maximum. This relative maximum also happens to be an absolute maximum. All absolute maximums are relative maximums, but not all relative maximums are absolute maximums. In a similar way, we say f of b down here, f of b. This was f of a. This is f of b. Is an absolute minimum. Is an absolute minimum of f of x, since f of b is less than or equal to f of x for all x that belongs to the domain of function f, or for all x on the domain of function f. This little symbol means belongs to, okay, or is a member of, or is an element of. All right. All right, so that's an absolute minimum point. This also is a relative minimum point, but it's also an absolute minimum point because there is no point on the graph lower than this point. So, relative or relative or local maximums or minimums, and absolute maximums and minimums for the graph of the function. All right, let's see what time it is now. 12:59. All right, we're going to go to our textbook here. And try a problem out here. Let's see if we can go to our textbook. And go to page 259. It doesn't like me doing that. So we'll just go to section 2.7 here. Okay, page 259. As always, please do spend time to look through the examples in all the sections that are covered in class. That will greatly enhance your understanding of what is going on. All right, so 97. All right, let's try this one first here, number 89. And this is going to be classwork number 1, ladies and gentlemen. Classwork number 1, problem 89. I want you to, using the graph of this function, determine the intervals on which the function is A, increasing, B, decreasing, and C, constant. Please write those intervals using interval notation. Problem number 89. This open hole here on the graph means that the point -33 is not actually a point on the graph. That point -33 is not actually a point on the graph. Go ahead and do that problem. I'll give you a minute or so. Problem number 89. Indicate the intervals on which the function is increasing, decreasing, and constant.
I had a question.
Fire away.
So for the test, are we gonna have a day like where we come in on Zoom and like ask questions and review how we
Tuesday.
did?
Next
Tuesday?
Tuesday is set aside for your questions, okay?
Okay. And if we don't have any questions, do we still?
I can just pop in and record your name and then you can pop out, okay? But Tuesday, I'm just setting aside for your day, okay? If you have any questions, then you might want to dial in when I'm online from 12:30 to 2:20, okay?
Yeah. And then is Thursday just starting chapter?
Oh yeah, chapter 3. All righty. How are we coming on this problem? We all done with number 89? So on what interval is the function decreasing? Anybody? On what interval? Decreasing.
-3 to -2.
-3 to -2, exactly. Because on that interval, from -3 to -2 on the x-axis, we are on this graph here. We're falling down from left to right. We're falling on the graph. Okay. So yeah. Well, let me see here. What the heck? Yeah, decreasing would be B's answer from -3 to -2. You are correct. On what interval are we constant? Is the function constant?
-2 to 2.
-2 to 2. And on what interval is the function increasing? That'll be from +2, well, not including +2, but on the interval of all real numbers greater than 2, correct? From 2 to infinity, not including 2. All right, so increasing and decreasing. Any question about how we can identify in what intervals a function is increasing or decreasing? All right, that was classwork number 1 there. Okay. All right, let's see what else we got here.
I have a question.
Yeah,
Clarify, we don't use brackets.
no brackets. Always just open, they're open intervals, okay? Yeah, intervals of increasing, decreasing, or constant nature of a function are always open intervals, no brackets.
And you said that was classwork 1?
Yeah, number 89. Yep, 89. We all got that one there? 89. Okay, now all right, so ladies and gentlemen, problem 101 is classwork number 2. I want you to indicate where we have any relative or local maximums or minimums. And I also want you to indicate, do we have any absolute maximum or absolute minimums? Okay, problem 101. I want you to indicate what points qualify as being relative or local minimums, maximums, or absolute maximums or absolute minimums. All right, go ahead and do 101. Classwork 2. All right, so let's take a look. Can anybody identify for me what points would be classified as relative minimums? Relative minimums.
-2, 4, and positive 2, 4.
Okay, -2, -4, correct?
Yes, that's what I meant.
And +2, -4, exactly. Those are relative minimums. Do any of these relative minimums also qualify as being absolute minimums?
Yeah.
Would they both be?
Yeah, they both are absolute minimums. They both are the absolute lowest points on the graph. So not only is -2, -4, +2, -4 relative minimums, they're also absolute minimums. Any
How do you-
relative maximum, what's that?
How do you know if it's in like what's the difference between a relative and an absolute?
Okay, a relative minimum. Let me see if I can show you an example here. Well, an absolute minimum is the lowest point on the graph of any point on the graph anywhere. It is the lowest point on the graph. That's called an absolute minimum. Or you can have a relative minimum that is not an absolute minimum. So, for instance, let me show you this example here. So if you have this graph right here, graph of this function here, okay, this point here, a f of a, that is a what? That's a relative minimum. But it's not an absolute minimum because the absolute minimum would be down here. This is an absolute minimum down here. Okay, so this point here, CF of C, is an absolute minimum. It's also a relative minimum, but it's also an absolute minimum because it's absolutely the lowest point on the graph. There is no point lower than that point. Does that answer your question?
Yeah.
Okay. So relative maximum. Do we have any relative maximums? Relative maximum, relative or local maximum?
Would it be 0, 0?
0, 0, the origin. Is 0, 0 also an absolute maximum?
Yeah.
No.
No. In fact, does this graph even have an absolute maximum?
No.
There is none. Because if I choose this point here, you can choose a point higher than that point, and I can choose a point higher than that point, and you can choose a point higher than that point. We can go on forever because this graph goes up forever. There is no absolute maximum on this graph. There's a relative maximum right here, but there's no absolute maximum. There's relative minima right here and here, and you also have absolute minima right here and here. Okay, but there's no absolute maximum. All right. So that was classwork number 2 here.
Can you show how the answers one more time? I had missed the first one.
Yeah, right here. So at x equals -2, the function has a relative minimum of -4. At x equals 0, the function has a relative maximum of 0. At x equals +2, the function has a relative minimum of -4. And I might also add that at the points of -2, -4, and +2, -4, we also have absolute minimums. So your relative minimums also happen to be absolute minimums for this graph.
So how do you want us to answer it like that on the classwork?
Well, you can just represent it by an ordered pair if you want. Your author is being a little bit more discriminate here because your author is indicating where the relative minimum occur. The relative minimum occur at -2 and at +2. And what would be the relative minimums? Well, they would be -4. So x equals -2 and x equals +2 indicates where the relative minimums occur. Whereas f of -2 and f of 2 both being -4 indicate what the relative minimums would be. The relative maximum occurs at x equals 0 and would be f of 0, which is 0. Okay, does that make sense there?
Yeah, I'm just a little bit confused. So we don't have to answer all four, like relative and local minimum. There isn't all, I'm just a little bit confused on this problem. I'm sorry.
Okay, so another way we could indicate where these extrema hang out is like this point down here. This is a relative minimum, correct? Right here.
Yes.
And you could indicate that you have a relative minimum at -2, -4. Okay.
Oh, okay,
that would be
okay,
good
I
enough.
get it. I see.
And
Thank
you
you.
have a relative maximum here at 0, 0. And you can just indicate it as an ordered pair if you want, 0, 0. This would be a relative minimum down here, which is +2, -4. All right. There is no absolute maximum. There's absolute minimums. They would be this point here and this point here. All these are also absolute minimums, but we don't have any absolute maximum. All right. Any
Okay,
other
thank you
questions
very
on that? All right. Okay. All right. So let's see. I think we're good on that. Now 113. Okay. I think we're good on that. Let's see. I don't think there's anything else here. All right. Let's see what's going on here. All right. Okay, we're good. Okay, so let's move on to the next section. The last section this afternoon is section 2.8. And 2.8 is entitled The Algebra of Functions. Right. All right, suppose we're given two functions. Some function f and some function g. Okay. Now, I can form brand new functions from these pre-existing functions. I can form what's called a sum function, f plus g of x, and this is called our sum function. It's formed by taking the output of function f and adding it to the output of function g. So f plus g of x, this sum function is formed by adding f of x and g of x together. That's called your sum function. All right, we can form what's called a difference function, namely f minus g of x. And this brand new function is formed by taking f of x and subtracting off g of x. We can form what's called a product function, which is f times g of x, which is going to be formed by taking f of x and multiplying it by g of x. And yes, we can form a quotient function, which is f divided by g of x. And it is going to be f of x divided by g of x. Now we must insist, since we're dividing here, that our denominator, g of x, never be equal to 0. That's got to be true for all x, okay? So we must impose the restriction on g of x that it can never be 0 for any x, because if it is, your quotient function is undefined. All right, so algebra of functions. You can add functions together, subtract them, multiply them, and divide them to form new functions. Now, how does the domain of these brand new functions relate to the domains of the individual functions? Well, the way it works is this. The domains of the sum, difference, product, and quotient functions are always going to be the intersections of the individual functions. the intersections of the domains of the individual functions. So it's going to be the domain of function f intersected with the domain of function g. So you have to take the intersection of the domains of the individual functions in order to find the domain of, you know, the sum, the difference, the product, and the quotient function. For the quotient function, there's another restriction. For the quotient function, if for f divided by g of x, if g of c is equal to 0, then c cannot be in the intersection of the domains of the initial functions. So if for the quotient function, f over g of x, or f divided by g of x, g evaluated as some real number c is 0, then we must exclude c from the domain of the quotient function. That's what this is saying. C cannot be a member of, or an element of, or belong to this domain. Okay. So we got to be a little bit more careful when we have our quotient function there. All right. Okay. Suppose I give ourselves some specific functions to work with here. And but before I do that, I want to point out a very important fact here. For any polynomial function, and this is a general way of representing an nth degree polynomial function. So this is a general way of representing any nth degree polynomial function, where a's are just the coefficients and x's are the variables, okay? For any polynomial function, any function that looks like this is called a polynomial function. It's a well-known fact that the domain is always a set of all real numbers, and that's always true. So given any polynomial function, its domain is always all real numbers. That's always true for polynomial functions. So some examples of some polynomial functions, 2x plus 3. This is a linear polynomial function. Its domain is all real numbers. Here is a quadratic polynomial function. Its domain is also all real numbers. It doesn't matter what degree your polynomial function is. As long as if it's a polynomial function, the domain is all real numbers, okay? So that's always true. All right. Suppose that we're given some functions. F of x is defined to be this linear function 2x. H of x is defined to be this quadratic function x squared minus 4x. And k of x is defined to be this radical function, which is the square root of x minus 1. Suppose I want us to find f minus g and evaluate it at 3. This is saying f minus g of 3. What is this saying to do? Well, this is saying not only are we to form the difference function, but we're also to evaluate it at 3. So this is saying or suggesting that we take f of 3 and subtract off g of 3. That's what it's saying. F of 3 means we evaluate function f when we put 3 into it, meaning f of 3 is going to be 2 times 3. G of 3 means we evaluate function. Did I say g here? Oh gosh, I meant h here. Tell you what, we're gonna have to change this from h of x to maybe g of x. Let's call this g of x instead here. That'll fix that. Sorry about that. Let's call this g of x. All right, so g of 3 means we put 3 into function g. That means we got to put 3 in here and here. Now we are to subtract off the whole function, so make sure you enclose it inside parentheses. So it's going to be 3 squared minus 4 times 3. Hence, we're gonna have 6 minus, this is gonna be 9 minus 12. 6 minus a -3, which is gonna be 9. So F minus G of 3 is 9. Any questions how we evaluated that difference function at 3? All right. Now suppose that I want you,
So are we just ignoring the K?
yeah, we're not using it, not for this problem. No. I will be using it for another one. All right, let's try let's find G plus F of X. What is this going to be? G plus F of X. This is going to be G of X plus F of X. It's our sum function, which is going to be nothing more than X, G of X, which is this guy right here, plus F of X, which is 2X. So we get this brand new function called X squared minus 2X. That's G plus F of X. All right, what would be F times G of X? Suppose I want us to find this. This is going to be F of X times G of X, which is to say F of X is 2. I got to do that down here, which is to say 2X times G of X is X squared minus 4X. And we can distribute here to simplify this a little bit. So we'll have 2X cubed minus 8X squared. That's a brand new function called F times G of X. All right. Suppose we want to find the quotient function, K divided by G of X. What is going to be this new function? Well, it's going to be K of X divided by G of X. Well, what's K of X? K of X is the square root of X minus 1. And G of X is X squared minus 4X. That's a brand new function called K divided by G of X. Any questions about any of these here? All right. So I gave you some functions and we just formed some new functions and evaluated one of our new functions at a specific value here. Okay. All right, let's try this one here. Suppose that we're given these functions here. M of X is equal to X plus 3. That's just a linear polynomial function. N of X is equal to X squared minus 9. That is a quadratic polynomial function. And suppose that P of X is this radical function, the square root of X plus 1. So problem number 1, suppose that I want us to find this new function n minus m of x. And I also want us to find the domain of this new function. The domain. Well, n minus m of x is going to be the new function n of x minus m of x. N of x is x squared minus 9, and we're going to subtract off m of x, which is to say we subtract off x plus 3. Distributing the negative sign throughout, we have x squared minus 9 minus x minus 3. So our new function n minus m of x is going to be the brand new function, which is x squared minus x minus 12. Minus 12. Okay. Questions how we form this new function n minus m of x?
No, but It cut out for the last one. Do you mind going back real quick so I can just see the answer?
For which one?
The last one you did.
The last one was over here. That's the last
Yeah.
one I did there.
Is that just the answer? The x minus 1 over x to the second?
Yep, k divided by g of x is going to be k of x divided by g of x. You got a brand new function here. That's it.
You wouldn't try and go any further to solve that?
No, there's nothing else you can really do with this. And I don't want you to evaluate it for any specific input value. Now, if I put a number in place of x here, like 5, that means you'd have to what? Actually evaluate this new function at 5 by putting 5 in here, here, and here, correct? And cranking it out. True?
Yeah.
But I just want you to form the function in general, all right? Called a quotient function of k and g.
All right, thanks.
All right. Now, what is the domain of this new function n minus m of x? Well, the domain of this function n minus m is going to be the intersection of the domains of function m and n. Well, what's the domain of function n? N being a polynomial function. The domain of a polynomial function is all real numbers always. So we're going to intersect that with the function, or excuse me, the domain of function m, which also is a polynomial function. So its domain is all real numbers. So what's the intersection of all real numbers with itself? It's the set of all real numbers. And that would be the domain of our new function called n minus m. So it looks like this new function n minus m of x is defined for any real number. It doesn't matter what number you put in for x, you will always have a defined real number output value. Okay. All right, next one here. Find m times p of x and also the domain of m times p. Well, m times p of x is going to be formed by taking m of x and multiplying it by p of x. Well, what's m of x? M of x is defined to be x plus 3, and p of x is a square root function. So m times p of x is going to be m of x, which is x plus 3, times p of x, which is the square root of x plus 1. That's our new function called m times p of x. And the domain of this new function, m times p, is going to be the intersection of the domains of function m and the domain of function p. Now, what's the domain of function m? Remember, m of x was just x plus 3. Well, since m of x is just a polynomial function, its domain is all real numbers. But what's the domain of function p? Where p of x is the square root of x plus 1. Well, a square root can become undefined if you ever have a negative appearing underneath the square root. So we must insist that this x plus 1 always be greater than or equal to 0, which implies that x better always be greater than or equal to 1. So the domain of function p is all real numbers 1 or larger. Now, what is the intersection of these two sets? What's the overlap between these two sets? Anybody want to weigh in? What would be the intersection of these two sets? Well, the intersection of these two sets is just going to be this set right here. So this would therefore have to be the domain of your new product function, m times p of x. So the domain of this function would only be all real numbers greater than or equal to 1. In other words, you cannot put any number into this function here that is less than 1. If you do, then you'll be taking the square root of a negative number. And the square root of a negative number is no longer a real number. It's an imaginary number, undefined. Okay. So that would be the domain of our product function. Any questions about how I'm forming these domains of these new functions we're forming? Okay. Using those same functions, let's form a quotient function. Let's form the function p divided by n of x. Well, this is going to be the brand new function called p of x divided by n of x. Well, what's p of x? P of x was the square root of x plus 1, correct? N of x was defined to be x squared minus 9. So we have our brand new function called p divided by n of x. What's the domain of this new quotient function? Well, it is going to be the intersection of the domains of the individual functions. Well, what's the domain of function p? Where p of x is equal to the square root of x plus 1. The domain of function p, we already arrived at that in the last problem. It's got to be all real numbers greater than or equal to 1. What's the domain of function n? Where n of x is x squared minus 9. Well, being a polynomial function, it's what? It's all real numbers. So, ladies and gentlemen, so far, it looks like the domain of our quotient function is the intersection between these two sets. Which is just this set right here. But we're not done, because this cannot be the correct domain. Because we have a quotient function, and we have to be extra careful now in the sense that our denominator can never be equal to 0. So this x squared minus 9 must never become 0, because if it does, our quotient function is undefined. So we need to impose another restriction on this domain for this quotient function. We must say that x squared minus 9 better never be equal to 0. Because if it is, we're dividing by 0, function's undefined. This implies that x squared better never be equal to 9, which implies that when we take the square root of both sides of this thing, implies that x better never be equal to positive or negative 3. So we have got to exclude positive and negative 3 from this domain here, this set. Now, negative 3 is not an issue, because negative 3 is not even in this set. We don't have to worry about it. But positive 3 is. So this is no good. We got to kick positive 3 out of here. It cannot be in the domain of this quotient function. This is not the correct domain. The correct domain of our quotient function must be all real numbers greater than or equal to 1, but not including 3. You cannot include 3. So the domain would be including 1 up to 3, not including 3, in union with not including 3 up to positive infinity. That would be the domain of this quotient function. Now, another way to represent domains, ladies and gentlemen, is you could use what's called set builder notation. You don't always have to use interval notation. So another way I could have represented this domain of this quotient function is I could have said it's the set of all real numbers x, such that x must be what? Greater than or equal to 1, and x cannot be equal to 3. So we could have just as well written a domain using set notation here as opposed to interval notation. These are saying the same sets, though. They're equal. Okay. All right. Okay. All right, there is one other operation that we can subject functions to. We've seen how to use the addition, the subtraction, the multiplication, and division operators to form new functions. But there is one more operator. It's called the composition operator. Okay. So, ladies and gentlemen, given two functions, f and g, whatever they are, we can form a new function called this function right here. And this little open circle is called the composition operator. So we would read this as f composed with g of x, f composed with g of x. And it's going to be the brand new function called f of g of x. Now, one way to think about this composition operator is to maybe think about it in this regard here. You could think of these functions as being like little machines, okay? First, we're going to throw x into function g, or machine g here. We're going to throw x into this function or machine called g. G is going to operate on its input according to its definition. It's then going to output something called g of x. And g of x then, g of x is now going to be fed into another machine called machine f, or function f. And function f is going to operate on its input called g of x according to its definition. And it will output something called f of g of x. That's what composition of a function does. It takes the output of one function and feeds it into another function. Now, what you got to be careful of is this. Multiplication is totally different than the composition of functions. So f times g of x is not even related to f composed with g of x, no relationship whatsoever. They do entirely different things. F times g of x is multiplying the functions together. F composed with g of x is taking the output of function g and feeding it into function f. It's not multiplying these functions together. So be careful there. Don't get multiplication confused with composition. In a similar fashion, we can form this function, g composed with f of x. This is read as g composed with f of x. It's going to be the new function, g of f of x. It'll just reverse things. This will be function f and this will be function g. First you throw x into function f and out comes something called f of x, and then f of x becomes the input into function g. That's called g composed with f of x. All right, so that's called your composition operator there. And maybe we can show ourselves some examples. But before I do that, I want to talk about what the domain of these composition functions has to be. All right. For the new function f composed with g of x, here's how the domain works for this new function called f composed with g of x, which is f of g of x. If, ladies and gentlemen, x is in the domain of function g, and f of g of x and g of x is in the domain of function f. If that's true, if these two things are true, then we say that x is in the domain of f composed with g. So in order to be in the domain of f composed with g, some number x has to be in the domain of function g, first of all. And therefore, and also g of x has to also be in the domain of function f. If just one of these fail, if one of these conditions fail, then x is not in the domain of the composition of f and g. For g composed with f of x, which is the new function g of f of x, it works this way. if x is in the domain of function f and f of x is in the domain of function g, then we can say that x belongs to the domain of g composed with f. If just one of these fails, if one of these fails, one of these conditions fails, then x is not in the domain of g composed with f. Both these have to be true for this to be true. That's how the domains of these composition functions work. All right, let's have a little bit of fun now. Any questions about this composition operator and what it does to functions here? Let's look at a specific example now. Theory is great and everything, but examples are better. Let's just let f of x be defined to be, let's say 5x, and let's let g of x to be defined as 2x plus 7. First of all, let's just find f composed with g of x. Let's find this new function called f composed with g of x. How do we do it? Well, f composed with g of x is going to be the new function, which is going to be f of g of x. So that means we're going to throw x into function g first, and out comes something called g of x being 2x plus 7. This 2x plus 7 is going to drop in and take the place of g of x now. Well, as I'm in this 2x plus 7, which is the output of function g, now becomes the input into function f. So this 2x plus 7 here is going to come over here, and it's going to drop. It's going to come over here, and it's going to drop in wherever you see x in the definition of function f of x. So to evaluate function f at 2x plus 7, it's going to be 5 times 2x plus 7. You have your brand new function called f composed with g of x. It's this function right here. And you can distribute the 5 inside if you wanted to. And we got that. Any questions how, given functions f and g, I found f composed with g of x? Any questions how we found that new function? F composed with g of x. Any questions? Let's turn it around now. Let's try to find g composed with f of x. Well, this is going to be the brand new function g of f of x. Which means we first throw some value x into function f, and out comes f of x. Well, what's f of x? It's 5x. So 5x takes the place of f of x. 5x, the output of function f, now becomes the input into function g. So this 5x now, okay, takes the place of x, wherever you see x in the definition of function g. So g evaluated at 5x is going to be 2 times 5x plus 7. Hence, you have the brand new function called g composed with f of x, which is to say it's going to be 10x plus 7. Any questions how we got that new function, g composed with f of x? All right. Now, what would be the domain of f composed with g? Well, suppose I take some value x. In order for x to be in the domain of f composed with g, x has to be in the domain of function what? Into what function am I putting x in first if I'm talking about f composed with g? Is x going into function g first or function f? What's the case here? F composed with g of x. Is x going into function g first or is it going into function f first? It's going into function g here first. And then the output of that, called g of x, becomes the input into function f. So x, if x is in the domain of function g, This would have to imply then that f of x would have to be in the domain of function f, in order to imply then that x would be in the domain of f composed with g. Okay. What is the domain of function g? Well, function g is a what? Polynomial function. And so its domain is what? All real numbers. And if you take a real number and evaluate function f at that real number, what do you get? What's the domain of function f of x? It's also all real numbers. So it seems to me, ladies and gentlemen, that you can choose any real number and it will always be in the what? The domain of the composition of f composed with g. So the domain of this new function f composed with g is all real numbers. It's all real numbers. You pick any real number, it will be in the domain of function g, guaranteed, because its domain is all real numbers. And if you evaluate function f at any real number, you know you're going to get what? Any real number, because the domain of function f is also real number, all real numbers. That's why the domain of this f composed with g function must also be all real numbers. In a similar fashion, what would be the domain of the function g composed with f? Well, for g composed with f of x, you're putting x first in the function f, and then the output called f of x becomes the input of the function g. So first of all, x, in order to be in the domain of g composed with f, it would have to be in the domain of function f. I think that's obvious because the domain of function f is all real numbers. So you know any real number is going to be in there. But this would also then have to imply then that g of this would then have to imply that f of x would have to be in the domain. Let's see here. You know what here? I did not say this right. This should be g of x would have to be in the domain of function f. Yeah. So for f composed with g, if x is in the domain of g, g of x would have to be in the domain of f. And if that's the case, then it's enough to say that x is in the domain of f composed with g. Here we have g composed with f. So if x is in the domain of f, this would have to imply then that f of x would have to be in the domain of function g. And if that's the case, if both these are true, then that would be enough to say that x is in the domain of g composed with f. There you go. All right. But ladies and gentlemen, if you choose any real number, it's obviously in the domain of f because the domain of f is all real numbers. And if you evaluate function f at any real number, you're going to get a real number. So obviously this will be in the domain of function g. So I think it's obvious to say then that x would be in the domain, therefore, of g composed with f. So all real numbers is the domain of g composed with f also. Okay. All right. All right, let's look at these functions. Suppose f of x is defined to be 2x minus 6, and g of x is this rational function 1 over x plus 1. First, I want to find f composed with g of x. And I also then want to find the domain of this new function called f composed with g. All right, first of all, let's form this new function. What is f composed with g of x? It's going to be the new function f of g of x. That means we put x, first of all, into function g, and out comes g of x. What is g of x? It's 1 over x plus 1. So 1 over x plus 1, which is g of x, then becomes the input into function f. So this 1 over x plus 1 now needs to go into function f, meaning it has to drop in here. So 1 over x plus 1 has to drop in right here in the function f. So therefore, function f evaluated at 1 over x plus 1 is going to be 2 times 1 over x plus 1 minus 6. That's what you get for f composed with g of x, brand new function here. And this function would be 2 over x plus 1 minus 6. Brand new function. This is a brand new function called f composed with g of x. Now, ladies and gentlemen, what would be the domain of f composed with g? What would be its domain? Well, first of all, I will choose some real number x that would be in the what? Would have to be in the domain of function g. X goes into function g first, and then g of x goes into function f. All right, well, what's the domain of function g? What is the domain of function g? G being this up here. Well, the domain of function g must not include what number? When would this become undefined, this rational function here?
-1.
-1. So the domain of function g can be the set of all real numbers x such that x cannot be equal to -1. I'm just going to use set builder notation to represent the domain of function g instead of interval notation. I mean, interval notation would be this down here, -infinity to -1, not including -1 in union with, not including -1 to positive infinity. That's saying all real numbers except -1. These sets are saying the same thing. This is called set notation. This is called interval notation. Okay. So if I choose some value, okay, it had better be in the domain of g rather, which means I cannot choose what? I can choose any real number for x except what? I cannot choose -1 because -1 would not be in the domain of function g. So suppose I choose some real number other than -1. Then if I evaluate function g at that value, will it be in the domain of function f? So if I evaluate function g at x, some number other than -1, well, you know I'm going to get some real number here. And why do I know that this real number is going to be in the domain of function f then? Because what's the domain of function f, being a polynomial function? It's all what? All real numbers. Okay. And so what's the only restriction on the domain of f composed with g? When would both these conditions, when would at least one of these conditions fail? It would fail if I choose a real number that is equal to what? -1? Because -1 would not be in the domain of function g. So -1 could not be in the domain of the composition of f and g. So the domain of this function f composed of g is all real numbers except -1. So therefore, we're going to say all real numbers except -1, and you could use interval notation to denote that. Or if you want to use set builder notation, that would be okay. The set of all real numbers x such that x is not equal to -1. Either way.
We're not using brackets on the next to the -1.
No, no brackets on -1 because -1 cannot be included. All right, because -1 cannot be in the domain of function g, because if it is, then this function will be undefined at -1, correct? The denominator goes to 0. So that's why you cannot include -1 in interval notation. You have to use parentheses here. Make sense? So that would have to be the domain of this composition of f and g. All real numbers except -1. Okay. All right, let me see if there's another one here. All right, let's take a look at this next one here. All right, so we got that one there. All right, so suppose that we're given this function k of x, which is x over x minus 2. And we're given m of x, which is 6 over x squared minus 1. So both these are rational functions here. Suppose I want to find the new function k composed with m of x. And I also want to find the domain of k composed with m. Okay. So how do we do that? Well, k composed with m of x is going to be the brand new function k of m of x. So we throw x into function m first, and out comes what? M of x. And m of x is 6 over x squared minus 1. So this 6 over x squared minus 1 becomes m of x. Well, that's to say that 6 over x squared minus 1 becomes the input into function k then. So 6 over x squared minus 1 becomes the input into function k, which means it has to come up here and drop in here and here. So therefore, our new function k composed with m of x is going to be 6 over x squared minus 1 over 6 over x squared minus 1 minus 2. That's your brand new function called k composed with m of x. Now we probably want to simplify this. This looks really nasty. This is a complex fraction. And to simplify this complex fraction, all I have to do is multiply the numerator and denominator of this fraction by the least common denominator, which is to say we multiply top and bottom by x squared minus 1. I'm going to multiply the whole thing by x squared minus 1. Now this x squared minus 1 is going to multiply by this fraction, and the x squared minus 1s are going to drop out, leaving you with just 6. In your denominator, x squared minus 1 times this fraction, the x squared minus 1s drop out, leaving you with 6. But you still got the minus 2 that has to be multiplied by the x squared minus 1. So we have 6 over 6. Now distributing the negative 2 inside the parentheses, we got minus 2x squared plus 2. So our brand new function k composed with m of x simplifies down. Okay, simplifies down to 6 over negative 2x squared plus 8, correct? Plus 8. That's your brand new function called k composed with m of x. All right. Now, if we look at our end result here, k composed with m of x, we would ask ourselves this question initially. When would this thing be undefined, this function? Well, it's going to be undefined when the denominator is equal to 0. So let's take this negative 2x squared plus 8, and we must insist that this never be equal to 0. Because if it is, we're dividing by 0, the whole thing's undefined. So let's solve for x here. So we subtract 8 from both sides. Divide both sides by negative 2. So x squared better never be equal to 4. Take the square root of both sides. Don't forget the plus or minus square root of the number side. So x can never be equal to positive or what? Negative 2. X cannot be equal to positive or negative 2 here. All right. Now, let's look at what's going on here. X goes into what function first for k composed with m of x? X is going to go into function m first. So maybe we better take a look at the domain of function m, which is up here. This is function m here. We better look at the domain of function m. So since m of x is equal to 6 over x squared minus 1, we got to make sure that this denominator x squared minus 1 is never equal to 0, which means x squared can never be equal to 1, which means x can never be equal to positive or negative the square root of 1, or x can never be equal to positive negative 1, correct? So the domain of function m must exclude positive and negative 1. So the domain of function m is the set of all real numbers x such that x cannot be equal to positive or negative 1, using set builder notation to denote the domain of function m here. All right. So I cannot put positive or negative. So positive and negative 1 cannot be in the domain, ladies and gentlemen, of this function here. Oh, excuse me, of our composition function here. Cannot be. Why? Because positive and negative 1 do not even get past this first function m. Because positive and negative 1 are not found in the domain of function m. So therefore, they cannot be in the domain of our function k composed with m of x. Now, we said that we also said that the set of numbers for which this function is going to be defined is all real numbers except positive or negative 2. So initially, it looks like the domain of this, after going through this, the domain of this new function k composed with m, looks like it's all real numbers except what? Positive or negative 2, correct? It looks like this right here. This is saying all real numbers except 2 or negative 2. But we must also insist that we cannot have what? Positive or negative 1 in here. Because positive or negative 1 is not even in the domain of function m. And remember, in order to be in the domain of k composed with m, a real number has to satisfy both these conditions. It has to be in the domain of function m. And this would also then have to imply that m of x would have to be in the domain of function k.
Could you write out what the domain of n would look like in not in the set builder notation?
Not set notation? Yeah.
Yeah. Can you write
Well, the
the other?
domain of m in interval notation would be negative infinity up to negative 1, but not including negative 1 in union with not including negative 1 up to positive 1, not including positive 1, and union with not including 1 up to positive infinity. That would be the domain of function m, interval notation. This is saying all real numbers except 1 and negative 1. Okay. So the domain of k composed with m cannot just be this set here. Because why? Because 1 and negative 1 are found in this set. And 1 and negative 1 cannot be in the domain of this function k composed with m, because positive and negative 1 are not even in the domain of function m. All right? Function m does not have 1 or negative 1 in its domain. So we have to exclude those. And we have to toss them out. But we can also not have what? We can't have 2 or negative 2 in our sets either. Because if we have, let me see something here. Suppose I let x be positive or negative 1. And then I put positive or negative 1 in the function m of x. So if I evaluate function m of x at positive or negative 1, what am I going to get? I'm going to get 6 over positive negative 1 squared minus 1. And you know what this is going to give me here? This is going to give me 6 over yeah, 6 over 0. It's not even going to be defined there. Okay. So you can see that positive negative 1 causes function m to be undefined. And we knew that. That's why we stated the domain for function m had to be this here. So we cannot have positive negative 1 be in the domain of k composed with m of x. But we can also not have positive or negative 2 be in the what? Domain of function k composed with m of x. Can't have that either. All right. So therefore, what would be the domain of function k composed with m of x? Well, it can be all real numbers as long as the real numbers are not positive or negative 2, but also cannot be positive or negative 1. So how could you denote that domain, which seems rather complicated? Well, you could say the domain of k composed with m. Okay. Can be the set of all real numbers x. This is set notation, such that x cannot be equal to, you could denote it this way, cannot be equal to -2, or cannot be equal to -1, or cannot be equal to +1 or +2. That would be one way. That'd be the set builder notational way. All right. Now the interval notational way would be saying from -infinity up to -2, in union with not including -2, -2 up to -1, in union with not including -1 up to 1, in union with not including 1 up to 2, in union with not including 2 up to infinity. Okay, so that would be the domain of K composed with M of X. This is basically an elaborate way of saying all real numbers except -2, -1, +1, and +2. Right? That's what it's saying. It's saying the same thing as this is saying right here. Okay. Same thing. Okay. All right, so I gotta let's see here. I have a last classwork for you. Ladies and gentlemen, let's see if you can maybe try this last one out here. Okay, so we'll call this the last classwork here. So, f of x is going to be equal to 2x minus 6, and g of x is going to be equal to 1 over x plus 4. Okay, what I want you to do here for problem number 1 is I want you to find f composed with g of x. And problem number 2, I then want you to find the domain of f composed with g. Problem number 3, I want you then to find g composed with f of 5. Okay. All right, we'll call that the last classwork there. And your domain you can represent either way, either set notation or interval notation. That's up to you. All right, so, G of X and F of X having these definitions, F composed with G of X is gonna be F of G of X. Which means you put X in the function G first, and out comes G of X, which is 1/X plus 4. Well, 1/X plus 4 becomes the input in the function F now. So this 1/X plus 4 is going to come down here and take the place of X wherever you see it in the definition of function F here. So therefore, function F evaluated at 1/X plus 4 is going to be 2 times 1/X plus 4 minus 6. Minus 6. And there's your new function called F composed with G of X. You can just leave it like this. You could get a common denominator and, you know, combine this into one fraction if you wanted to, but you just leave it like that. Notice the domain of function G is all real numbers except -4. You cannot have -4 in the domain of this function G. You can represent it using interval or set notation. Now, so -4 is the only number that obviously cannot be found in the domain of F composed with G, because -4 is doesn't even make it past the domain of function G. All right, but you don't have to worry about anything else not being the domain of function F composed with G, because F evaluated at any other number is going to be defined, because the domain of F of X being a polynomial function is all real numbers. Okay, the domain of function F of X is all real numbers. So -4 is the only number that must be excluded from F composed with G. And you can represent it either way there. And finally, this last problem here, G composed with F of 5 is going to be G of F of 5, which means first we put 5 into function F, which means 5 goes in here first. 2 times 5 minus 6 is F of 5, which evaluates to 4. And then 4 becomes the input into function G, which means now you put 4 into function G right here for X. So a G of 4 is 1/4 plus 4, or 1/8. And that is G composed with F of 5. All right, I am out of time, ladies and gentlemen. So I will stay on the line for a couple minutes if you have any questions. I will open up the remaining sections in chapter 2 in Alex, and also the chapter 2 quiz in Alex. Make sure you do all the homework and quizzes first before you even attempt the exam. The exam will not be released till next Tuesday on chapter 2 on Alex. All right. So if there are no questions you have